This is an example of a classic physics problem set up here. The best thing to do when you hit one of these problems up is really try to grab what information you can. Think in terms of position, velocity, acceleration. So we're driving along in this car at 132 feet per second. So that is your initial velocity. So you want to kind of pull that out and say, my initial velocity, v of 0, is equal to 132 feet per second. We see a brick wall ahead of us. We're 400 feet from the wall when we slam on the brakes. Careful on this when we see the 400 feet from the wall. A lot of people want to use that as their initial position. Really, what's going on in this problem is your initial position is where you start the process of braking. And so your initial position on something like this is actually going to be 0. And then what you're going to do at the end is compare your final position to that 400 feet. So that's sort of a trap bit of information right there. Then we've got the last bit of data for us comes from the fact that we're decelerating. So notice that acceleration term at a constant rate of 22 feet per second squared. That second squared piece right there should really sort of bells and whistles tell you that you're looking at an acceleration. So what we know right now is our acceleration is a constant amount, and it's a negative 22 feet per second squared. So what this ends up being is one of those situations where we got to work our way back up the physics chain. So normally you would start at a position equation, and then we know that our derivative of position is velocity, and that our second derivative of position, our first derivative of velocity, is going to be our acceleration. And so this is where we're starting at the bottom here with our acceleration data, and what we're going to need to do is basically move up 2 layers here to get our velocity equation and then to get a position equation. And from that information, we should be able to tell if we're going to run into this wall or not. So first thing we'll do is we will take the antiderivative of our acceleration equation here. So negative 22 feet per second squared. We actually don't need the units as we're doing this part. So this is really just the antiderivative of negative 22. Again, the negative comes in this because we are decelerating. So we are slowing down. So they don't always put that negative on the number. We have to know that it's there. So to undo this, to get back to our velocity equation, we're just going to do our power rule. The antiderivative of a constant, numbers by themselves, gain a letter back, and then we have this plus c. So this is what our velocity equation is equal to. And so we'll do sort of an initial value process. We're going to go over here and we're going to find what our initial velocity is. So we know that when we plug in 0 to this equation for t, that we need all of this math to equal that initial velocity of 132. So out of here we get 0 times negative 22 is going to get us 0, so that's going to cross out, and we're going to end up with c equals 132. So we bring that information together with our velocity information, our antiderivative here, to come up with our velocity equation. So our velocity equation is negative 22 plus 132, that c we just found out. Well, in order to see if we go 400 feet, we are going to need to get a position equation. And so to do that, we are at the velocity level now, and we're going to need to take an antiderivative to go up a level to position. So we are going to take the antiderivative of our velocity equation, so negative 22t plus 132 dt. So we'll just be applying our power rule here. So add 1 to the power, divide by the new power. So we get negative 22t. There's an unwritten 1 right there. So we add 1 to the power, divide by that new power. Plus, again, numbers by themselves gain a letter back. And then again, we always get that plus c out at the end. So what we have here is our position equation. So I'm going to go ahead and simplify that down. The 2 and the negative 22 will cancel out. So we're really looking at negative 11t squared plus 132t plus c. So to get that final bit of information, we need to figure out what the plus c is on our position equation. So we go back to that original data and we say, okay, well, Our starting position when all of this happened was 0. So that means when I plug 0 into this equation for our t value, we actually want the answer to all of that math to equal 0. Well, that'll zero out, that'll zero out. We end up with c equals 0. So again, we put this data together, and we get out of here a position equation that says S of t equals negative 11t squared plus 132t. And then r plus c was 0, so we don't need to have that on there. So we've got a velocity equation, we've got a position equation. So what can we do with that? Well, you know that when you stop, as long as you don't hit that wall, the velocity of that point in time would be 0. So if we are going to go figure out when our vehicle stops, we actually just need to do a little algebra problem. We need to know when does the velocity equal 0. So negative 22t plus 132. So we're just going to go ahead and solve this whole thing over to get out what our velocity would be at that point in time. So we'll minus, or exactly, not what the velocity would be, what the time is when we stop. So we're going to figure out when our vehicle actually stopped. And again, we're hoping upon hope that we don't run into that wall. So let's see, divide by negative 22, divide by negative 22. Pop that into your calculator, and out of there, you're going to get 6. So what we know is that based upon this deceleration rate over here, our car will stop in 6 seconds. And now the real question comes in, what is our position at that point? So if we plug 6 seconds into our position equation, and what we come out with is greater than 400 feet, well then that means we didn't stop in time and we smacked into that wall. If our position that we come out of this with at the end is less than 400 feet, then we safely stopped and we did not hit that wall. So we're going to take our 6 and we're going to plug it into our position equation and see what we get out of here. So we would do S of 6 equals, plugging everybody into this position equation, we get negative 11. Instead of t, we have 6 squared plus 132 times 6. And now we will plug that into our calculator, and we would get out of there 396 feet. So we were able to stop our car at 396 feet, which was 4 feet short of the wall that was in front of us. So we stopped safely in this scenario. Again, one of the tricks to this is kind of understanding that your position, your initial position, is that point in time. If you think about it, you start here and you've got 400 feet before you run into that wall. So your initial position is 0. That's kind of the trick to the whole thing. But this physics example is pretty classic. You started your acceleration, get back your velocity equation, then use that velocity equation to get back your position equation. And then remember that when you stop is when your velocity is 0. So you go find that time, and then plug that time into the position equation to figure out how long it takes you to stop. Thanks for watching my video. If you liked it, please click that like button and subscribe. And also share it with your friends and anyone else you know who might be crying about an upcoming AP Calc test. You can find more videos from me, more sample AP Calc questions, and my complete AP Calc study guide over at my website, apcalcprep.com. Have a great one.